On November 9th, astronomers encountered an image that immediately unsettled long-standing assumptions about how small bodies behave in space. Captured after the object known as 3I/Atlas had passed perihelion, the frame showed a compact nucleus surrounded by a halo of dust and gas, but what dominated the scene were the jets. They were not curved, feathered, or diffuse, as cometary physics would predict. Instead, they appeared as razor-straight lines, sharp-edged and unwavering, radiating outward in multiple directions and remaining coherent for distances exceeding 1 million kilometers. Even more troubling was the fact that these jets maintained their alignment despite the object's confirmed 16-hour rotation period. According to every established model, such jets should have been twisted into arcs or smeared into spirals by the nucleus's spin. Yet here they were, pristine and linear, as if locked in place by a mechanism no one had anticipated. The November 9th image was not a simulation or an artist's interpretation. It was a direct astronomical observation processed through standard reduction pipelines at a major observatory. One feature in the frame, the so-called antitail, could be explained. This faint, broad streak pointed almost toward the sun, an optical effect caused by sunlight reflecting off dust particles positioned between Earth and the object. Antitails are rare but understood. The other jets, however, were something else entirely. They shot out at varying angles, unrelated to the sun's direction, and showed no hint of curvature or diffusion even far from the nucleus. Their geometry was so stark that it demanded explanation, not interpretation. Just months earlier, during July and August of 2025, astronomers had carefully measured the rotation of 3I/Atlas using coordinated photometric campaigns. By tracking subtle, repeating variations in brightness, they derived a light curve that revealed a rotation period of 16 hours, with an uncertainty of only a few hundredths of an hour. Multiple observatories independently confirmed the result, ruling out instrumental errors or background interference. This was not a guess, it was a solid, reproducible measurement. For a body several kilometers across, tumbling through space at interstellar velocity, this spin rate fell squarely within the normal range for comets. That normalcy is precisely what made the November observations so disturbing. Rotation matters because it sets the clock for everything happening on a comet's surface. Any jet tied to a fixed vent, crack, or active region should sweep around as the nucleus spins. Over time, that sweeping motion should imprint itself on the escaping material, creating arcs, fans, or corkscrew patterns. The longer the material takes to travel outward, the more pronounced the effect should be. For 3I/Atlas, dust particles were estimated to be moving at roughly 400 meters per second, a typical speed for cometary outflows. At that rate, reaching a distance of 1 million kilometers takes nearly 29 days. During that same period, the nucleus completes more than 40 full rotations. Under such conditions, straight jets are not just unlikely, they are mathematically forbidden by standard physics. When the Parnell Observatory team first processed the November 9th data, their reaction was immediate disbelief. They rechecked everything: raw images, calibration files, background subtraction, and projection effects. Nothing changed the result. The jets remained straight, narrow, and coherent. Internal reports labeled the phenomenon an anomaly, a term that soon spread through informal channels and research groups. Slack messages and lab notes from that week reveal a mix of excitement and unease. This was not a minor discrepancy that could be patched with a tweak to an existing model. It was a direct contradiction. The numbers made the problem unavoidable. A dust grain leaving the surface at 400 meters per second takes nearly a month to travel the length of the observed jet. During that month, the nucleus spins over 40 times. If the jet originated from a surface vent, each rotation should redirect the flow, producing a spiral or a series of overlapping arcs. Laboratory experiments and numerical simulations have confirmed this behavior repeatedly. The classic analogy is a rotating garden sprinkler or a person spinning with a hose. The stream curves. Straightness requires special conditions, such as a mission exactly along the rotation axis or velocities so extreme that rotation becomes irrelevant. Neither condition matched what was observed. The jets were too numerous, too widely distributed in angle, and too slow to fit those exceptions. Faced with this impasse, researchers began ranking possible explanations. One idea was that the object's rotation had slowed dramatically after the earlier measurements, effectively freezing the jets in place. But this ran counter to both theory and observation. Outgassing tends to spin comets up, not slow them down, and there was no photometric evidence for a sudden change in rotation. Another proposal involved sunlight-triggered jets that turned on and off with each rotation. In this model, each pass into sunlight would release a brief puff, producing a series of discrete segments along the jet. But the November images showed continuous, unbroken lines, not a string of beads. Fragmentation was also considered. Perhaps the nucleus had broken into multiple pieces, each producing its own stray tail. Yet no high-resolution images confirmed a breakup, and the light curve remained stable, suggesting a single dominant body. The most controversial hypothesis lingered at the edge of discussion, that the jets were not natural at all, but controlled, thrust-like emissions maintaining a fixed orientation in space. Even those who mentioned it treated it as a last resort, assigning it a probability well below 1%. Still, the fact that it could not be dismissed outright spoke volumes about how strained conventional explanations had become. Compounding the mystery were the object's orbital and compositional peculiarities. 3I/Atlas travels on a retrograde path almost perfectly aligned with the ecliptic, moving against a flow of planets while staying within a few degrees of their orbital plane. Such an alignment is vanishingly rare for interstellar visitors. Its size, estimated between 1 and 5 kilometers, makes it larger than Borisov and far larger than Oumuamua. Its excess velocity, above 23 kilometers per second, places it at the high end of known interstellar objects, carrying enormous kinetic energy through the solar system. The timing of its approach raised further eyebrows. The object passed near the orbits of Mars, Venus, and Jupiter while remaining poorly positioned for detection from Earth, shielded by solar conjunction until shortly before perihelion on October 29, 2025. Orbital modelers noted that such a combination of close planetary passages and delayed visibility was statistically unlikely. Spectroscopic observations added another layer of strangeness. The coma showed a high concentration of nickel relative to iron, a ratio far above solar system norms and more reminiscent, uncomfortably, of engineered alloys. Water vapor, the hallmark of cometary activity, was scarce, accounting for only about 4% of the coma's mass. As laboratories attempted to reproduce the jets under controlled conditions, failure became the norm. Spinning ice-dust mixtures in vacuum chambers produced plumes that twisted and dispersed. Simulations adjusted for surface roughness, outflow speed, and shadowed regions all predicted curvature. Even speculative ideas involving magnetic confinement found no supporting evidence. With each negative result, attention returned to the data itself. Telescope time was reallocated, debates grew sharper, and concerns arose about how the story might play out beyond academic circles. When requests for high-resolution NASA images were denied during a government shutdown, speculation intensified. Internal disagreements and vague references to national interest only fueled suspicion. Meanwhile, public fascination grew, linking the object's trajectory to famous anomalies like the WOW signal. Inside the scientific community, however, the mood was less playful. The mismatch between observation and theory was real, persistent, and unresolved. As things stand, 3I/Atlas sits at the boundary between explanation and mystery. Every natural model struggles to accommodate the straight, unwavering jets in the face of a rotating nucleus. Until new data are released and independently verified, the object remains a challenge to cometary physics, and a reminder that interstellar visitors may not always conform to our expectations. The universe, it seems, still has ways of slipping surprises past our defenses, forcing us to confront not just what we see, but how well we truly understand it.